Okay, this video lesson is a continuation of the last video lesson. The last one, what I was talking about was radioactive decay. Okay, it basically said what is radiation. Here we're going to look at why radioactive decay happens, and it's due to the unstable nuclei. I guess that's kind of what I talked about last time. Here we're going to look at the processes that cause an unstable nuclei to become more stable. And there's three reasons why that'll happen. One, that there's too many neutrons in the nucleus. So our nucleus is just too many neutrons in here, and it's going to find relief by releasing or reducing the neutrons, too many protons, or too many protons and neutrons. Okay, and that's going to happen with all elements 84 and above. Okay, so the first process we're looking at is beta decay. Now, beta decay is also known as beta emission because what it does is it emits what's called a beta particle. And a beta particle is nothing more than an electron. That's what this is supposed to be saying down here, by the way. This is a beta particle is a high-speed electron. That's all it is. So when you see beta, you think of electrons. Remember our notation for electrons, okay? So beta, electrons. Beta is referred to as a beta particle because Ernest Rutherford, who discovered what radiation was composed of, found this as the second particle, so he called it beta, the first one being an alpha, and then gamma, and we'll get to those a little bit later. So for right now, we're looking at just a high-speed electron, or what's known as a beta particle, being emitted from the nucleus, hence why we call these beta emission reactions. Also referred to as beta decay because it's a radioactive decay process, and it's decaying through beta emissions. So basically, beta is what's happening. All right, so why is it happening? Well, it has to do with the fact that there's too many neutrons in this particular scenario. So if we look at cesium-137, and we see that there's too many neutrons as a ratio, if we go back to that band stability, cesium is not one of those 279 stable nuclei. So what happens is cesium is going to go through beta decay, and it's going to emit a beta particle, which is the high-speed electron. How does it do that? It converts its neutron, the neutron that it has, okay, which has a 0 down here and a 1 down here, is going to convert into a proton, which is a 1 and a 1, and it also has an electron. Now, the proton stays inside the nucleus, hence why it goes from 55 to 56, and we create barium, and we get barium-137. And the electron is emitted and shot out of the atom, and therefore this is what the radiation is. So when we're detecting radiation, this is what we're hitting, and this is what hits you. So if you're getting hit with something that's radioactively decaying by beta particles, electrons are hitting you. Okay, so that's essentially what we've got. So beta emission or beta decay, high-speed electrons are emitted because a neutron is converted into a proton and an electron. As a result, atomic number is going to go up. So we're going to get the atomic number to go up. And again, when we balance these, we add the numbers on the top and add the numbers on the bottom. The mass numbers and the atomic numbers have to add on both sides of the equation. Carbon-14 is a radioactive element. Okay, it's a radioactive isotope of carbon. And what happens is it goes through beta decay. And the the neutrons convert into protons, and therefore we go from 6 to 7, another increase. So neutrons go to protons, we increase the atomic number, and again, a high-speed electron is emitted. And I wrote it with two different ways. Remember, we can represent the beta particle either this way or this way, whichever is up to you. You decide. And then we have alpha decay, and this is going to be the last one that we're going to look at. Alpha decay is the one that happens or occurs when you have too many protons and too many neutrons together. So this is for any element that's above 83. So 84 atomic number and above will have alpha decay processes going on. Essentially, what's happening here is an alpha particle is what's known as a helium nucleus. It's the helium nucleus because of the fact that it has two protons and two neutrons that it's going to emit. That's why we call it a helium nucleus. Two positive charges and two neutrons come out of the nucleus, and we have what's called alpha decay or alpha particles. Okay, this is the first one Ernest Rutherford found because it was the easiest, because it was the biggest. It was the heaviest particle with a mass number of 4 compared to the other particles that we saw. So we have lead-204 going through alpha decay, and again it's emitting an alpha particle as it transforms into mercury-200. Notice the mass number changes and the atomic number is going down. So we're reducing the protons. 2 protons, 2 neutrons. Now the thing about this is that this has a positive 2 charge because it's got 2 protons and no electrons to balance it out. That's going to make this molecule or this particle relatively dangerous. Okay, radon 20 or 226 goes through the same process. It loses an alpha particle, which is the helium nucleus. Again, you can write it in the two forms, whichever form you prefer, and that would be alpha decay. Okay, we get really heavy, sluggish particles. We'll talk about the differences between the particles in class. All right. So, the last thing I want to talk about, and then I'll wrap all this up with a slide that shows all the comparisons, is gamma rays, or gamma radiation, essentially. Gamma radiation is the energy that comes out of these reactions. So when you think about a chemical reaction, most chemical reactions produce heat. So we get fire from combustion reactions. So when we deal with nuclear reactions, these are going to be higher in the spectrum, and they're not going to release thermal energy or heat energy. It releases gamma radiation. And this accompanies a lot of these reactions. And it's energy. So there's no form of, there's no protons, no neutrons, no electrons. It is all energy. Just like in our chemical reactions, we don't really include the thermal energy, right? We didn't talk about thermal energy. We talked about heat being a product, and we can talk about gamma radiation being a product, but we don't really write these in the equations. I'm just kind of showing you here that the 0, 0, it really has no impact. You can go back and add this into all the other reactions if you want, but it really makes no difference, okay?